welcome to another bioCADDIE external webinar. My name is Kathy and I'm filling in for Cleo this morning. Dr. Hwanjo Yu is presenting for us today. Hwanjo Yu received his PhD in computer science at the University of Illinois at Urbana-Champaign in 2004. He was then, from 2004 to 2008, he was an assistant professor at the University of Iowa, and he's now an associate professor at POSTECH in South Korea. He's developed many influential algorithms and systems in the areas of data mining, database, and machine learning. And today he's here to talk about new challenges in big data, technical perspectives. Hwanjo, would you like to start?
Okay, thank you. Thank you for introducing me. This is Hwanjo. I'm an associate professor at POSTECH in Korea, South Korea. So today I'm going to present the new challenges in big data and the technical perspective. Okay. So to motivate my main subject today, let me first introduce a well-known example of big data application, that is social network mining. And as you know, there are over 1 billion users in the SNS space and communicating each other by text mainly. And people in the SNS space can easily communicate with others who are physically located far away. So more communications are accumulated every day at a very high speed. And by taking advantage of this big data that are accumulated every day at a very high speed, people have developed many interesting applications from this for the last decade. And one interesting application of social network is viral marketing. Viral marketing. What is this? Nowadays, the word of mouth effect in the SNS has more impact than TV advertising. It has more impact on the people's purchase decision, for example. This because people tend to listen to someone who they trust rather than an arbitrary person showing on the TV advertisement. So in the data mining community, researchers have formulated new kinds of problem called influence maximization. Influence maximization problem is to find the most influential people in the social network such that the amount of influence spread from the people is maximized in the social network. Okay? But it turns out that this problem is NP hard. That is, the optimal solution cannot be computed in polynomial time. So people have come up with many approximate solutions for this problem. And actually, we also developed one of the approximate solutions a couple of years ago. It is called IPA. IPA is scalable and parallelizable processing of influence maximization for large-scale social network. So this algorithm, the scalable and parallelizable algorithm for computing the K people whose influence spread is maximized. And this algorithm is actually currently not the state of the art anymore. Actually, better algorithms have been published after that, and new algorithms is still being kept proposed in the data mining community. But anyway, at that time, this algorithm was published. It ran like 10 times faster than the previous algorithm and used much less memory, and it was more accurate and it was more flexible by being able to be applied to more influence diffusion models, and also finally it was easily parallelizable. So if you use more cores, it speeds it up more. So, however, since this problem is very hard, this algorithm can run on social network of 5 million nodes only, a single machine. It couldn't run on a social network of like 100 million or a billion users. But nowadays the size of social network is it's very large. It is up to like billion users, right? But this algorithm simply couldn't hold this intermediate data in the middle, so due to this limited memory, it failed running on such large-scale social network. But, since this algorithm can be easily parallelized, why don't we scale up the algorithm to MapReduce, using MapReduce in multiple machines? This MapReduce is a parallel and distributed programming framework for processing big data. Since this IPA algorithm can be easily parallelized, one could think that it can also be easily extended to the MapReduce framework to scale it up to billion-node social network, right? Well, we tried very hard to scale it up to the billion-node using MapReduce, but it turns out to be very hard. We find that so something is easily parallelized does not mean it can be easily map-reduced. It means, data processing not totally equivalent to parallel data processing. It has something more than that. So how are they different? Well, let's go back to the history of traditional data processing frameworks such as enterprise DBMS, which is designed to process structured data. But this enterprise data is actually not a big data. In many cases, it can be handled by tens of machines. As the data volume and variety and velocity increase, people needed a new kind of architecture because existing architecture is just not scaled up easily. And this new kind of big data analysis architecture is layered into these multiple layers. From the bottom, see, it's a scale-out storage. And on top of that, there's a distributed file system. On top of that, database and data access method and high-level language and application. So this new big data analysis system has changed from the bottom, which is the storage architecture, in order to deal with this big data. So previously, this enterprise DBMS used a kind of centralized storage system such as SAN and NAS, where the servers are connected with a high-speed network. And this kind of proprietary system is highly reliable, but very expensive to upgrade or scale up. And this like SNS, like Twitter and Facebook, they accumulated multiple terabytes of data every day. And to handle such high speed of data accumulation in this centralized system, what can we do? Can you just buy multiple terabytes of hard disk every day and attach to this system? Well, that would be possible, but it's going to cost a lot. Scaling up this kind of proprietary system to handle such high velocity of data is very expensive. So people designed a distributed storage architecture where the servers are connected with a relatively slower network. But the servers are inexpensive commodity machines, and adding new machines to this network is relatively easy. So this scale-out problem becomes inexpensive. But as a side effect, data transfer between nodes becomes expensive. So we need a new kind of programming model. So this big data trend, such as high volume and high velocity, led this storage trend, which made this scale-out inexpensive, but data transfer expensive. So we need new kinds of programming model to minimize the data transfer. One key idea of such a programming model is to move operations instead of data. Because the size of operations is typically very small compared to the size of data. And if you think about this MapReduce, in fact such a framework where operations move from the master node to the data node, and data in the data node does not move. If you think about this map and reduce function, math function is designed in the master node, but they are actually executed in the data node. Right? Math function is designed in the master node, but executed in the data node. And the outputs of math functions travel through the network instead of data itself. So in this way, the data transfer over the network is minimized. And based on this, there are many big data sub-projects developed. So anyway, this MapReduce program must be designed based on these principles of minimizing data transfer. If you write a program in a brute force way without having these principles in your mind, you will face a serious performance problem. Probably you would find many tips from the internet to improve the performance, such as lower the workup reduce and compress the map's output and minimize iteration of broadcasting, and so on. If you think about these tips, these are actually to minimize the data transfer itself. So anyway, the programming becomes much harder, or I would say, we have to program it in a totally different way. So previously, our IPA algorithm, we failed to extend it to MapReduce because, straightforward extension of our IPA algorithm, parallel IPA algorithm, produced too many iterations and heavy data transfer from MapReduce. So many big data sub-projects have been built and still being built by many researchers, such as for batch process, Hadoop, and for iterative process, Hadoop and Twister, for streaming data, Storm, S4, Infosphere, and H-streaming. And for structured data management, there are many NoSQL DBMS developed, such as HBase, Cassandra, Dynamo, MongoDB. And also for big graph data analysis, there are also many engines, and just Pregel, Ugraph, Trinity, Neo4j, TurboGraph. And this TurboGraph is built by our group at POSTECH, and this is actually currently the fastest graph processing engine in a single PC. So this big data analytics research can be categorized into these three layers, like application layer and developing software platform and developing hardware infra. And people who build this software platform, such as MapReduce and NoSQL DB, are concerning about, they're concerning about how to minimize this data transfer. And what kind of applications they want to support, or what types of data they like to process, and what kind of tasks they like to optimize. They also have to consider about this data storage architecture. This storage architect is concerned about how to reduce scale-out cost, how to increase energy efficiency, and so on. And also, these application developers also concerned about what kind of platform, what kind of software platform they like to use, and what kind of platform they have to use to maximize the performance of their applications. Or is it possible to implement or optimize the application using a specific platform? Or if not possible, can we develop like approximate solutions? Finally, this SSD. SSD are currently dominating storage disk markets nowadays, although its cost is much higher than the typical HDD. And it has been just less than 10 years since SSD becomes so popular. But if you think about it, all these data processing technologies developed for the last century are optimized based on HDDs. So what does that imply? That implies all these data processing technologies developed for the last century have to be renovated in order to fully take advantage of this SSD's strength. So these are all new challenges in big data and the technical perspectives. So when this SSD came out at the first time, people did a lot of benchmark tests to compare its performance with HDD using Hadoop. And Actually, its performance, SSD's performance was not showing better in many tests. It turns out that the performance of SSD and HDD are similar here when we use the 100 gigabyte of data. Excuse me. But if we increase the data size to 200 gigabyte, SSD becomes better, right? And if we increase the data size further, SSD becomes better and better. And when we use 300 gigabytes of data, it executed like twice faster than HDD, even with half number of nodes. Here we used 16 nodes for SSD and 32 nodes for HDD. Still, HDD becomes twice faster. And, this kind of result could be useful when you make decisions on how to upgrade your system, right? Whether you like to spend your money on increasing number of nodes, or do you like to replace your HDD with SSD? But there are several ways to take advantage of this SSD in your system. First way is to replace all the HDD with SSD. This will cost a lot because SSDs are still expensive. So another way is to use SSD as a cache between HDD and memory. But this caching model has this problem of data duplication, right? So the space utility is not going to be good. The third way is to apply this tiering model by putting hot data to SSD and cold data to HDD. But then the data migration must be carefully designed. So the final model is to apply this distributed model where data migration occurs automatically. But this looks promising. So in fact, this caching model and tiering model and distributed model, all these models looks promising for HDD, right? But in reality, it turns out that people like to replace HDD with SSD. In this industry, like LinkedIn, Twitter, Amazon, Microsoft, Facebook. Because I think this industry like Facebook, Microsoft, money seems not a problem. So we eventually will replace all the HDD with SSD, I think. Then, eventually we will probably replace HDD with SSD in the future. Then, what else do we need to concern? What is the difference between HDD and SSD other than the price? The first is SSD support fast random access. Random access was very slow in HDD because HDD is a mechanical device, while SSD is electronical device, right? So since this random access was terribly slow in HDD, the graph processing was impossible with HDD because this graph processing is inherently incurs many random access to disks. So you will see that all these graph processing engine, they actually assume that the storage device are SSDs. And another good property of SSD is it supports parallel I/O. So CPU does not have to wait for I/O to return as it executes operations. So what does that imply? It implies that theoretically this disk I/O could be hidden if CPU operations are well designed with I/O operations by overlapping CPU process and I/O process. By this overlapped processing of CPU and I/O, this I/O cost can be offset by the CPU cost. And it turns out that this is actually a radical paradigm change of how to access the data between disk and memory. this overlapped processing of CPU and I/O is in fact a radical paradigm of new programming style to fully take advantage of this SSD to offset the I/O cost. So a couple of years ago, we developed a TurboGrafh, which is a disk-based graph processing engine in a single PC, and still this TurboGrafh is currently the fastest disk-based graph processing engine in a single machine. And this disk-based algorithm usually has this performance bottleneck in the disk access, because the disk access cost is usually the highest. And for this reason, if you think about it, all these database query processing algorithms are evaluated based on the number of disk accesses, right? There are many disk-based query processing algorithms you learn in database courses, right? If you think about it, they are evaluated based on their costs are computed based on the number of disk access, right? But in TurboGrafh, the disk access cost is hidden by this overlapped processing. So its performance is as fast as in-memory processing. And this, this performance is achieved by this overlapping the CPU processing and I/O processing, which hides this I/O cost. In other words, by this overlapped processing, we can achieve theoretically optimal performance, which is the in-memory processing. And 2014, we extended this TurboGrafh to compute this number of triangles in a graph, which is published in Sigma. And this year, we also developed fastest disk-based parallel matrix factorization algorithm by applying this overlapping processing of CPU and I/O. And this KDD paper is going to be presented next year in Sydney, and this work is a joint work with Professor Xiaochen Jiang, UC San Diego. Okay, now I'm going to start with the second part of this talk. So the first half of this presentation was about presenting the new challenges in the technical perspectives, such as the three layers, application layer and software platform layer, hardware layer, and what the researchers are concerning about when they develop new technologies for big data, right? And also there's an issue about SSDs. And also, when you do this big data programming, you have to concern about how to minimize the data transfer. These are all new technical challenges in big data. So now I'm going to start the second part of the talk, which is I will introduce a few interesting applications for search and mining. We actually developed several systems for search and mining in POSTECH, in our lab. So first I'm going to introduce a couple of search engines first. We developed at POSTECH. Search engine is relevance feedback search. This Google is kind of a general purpose search engine, right? That it does a really good job to find the target web pages that you're trying to search. And the ranking of this kind of general purpose search engine is computed based on the popularity of web pages. Of course, the detailed ranking algorithm is much more sophisticated than just the popularity. Like if you type like Cubase, which is a music editing software, Google finds the company page that developed this software, which is Steinberg. And Naver is the dominating search engine in Korea. It dominates over like 70% of search engine market in Korea. Because it is more sensitive to the trend change in Korea, so it searches well the trendy information in Korea very well. But honestly, it is not as good as Google for finding like external web pages. For example, if you type Cubase in Naver, it does not lead to this Steinberg homepage. These are all examples of general purpose search engine, right? There are other types of search engines, such as product search engine. This kind of product search engine needs to be more sensitive to catch users' preference. So user may have different preferences, right? So it needs to interact with users to figure out, for example, which brand the user prefers, or the price range or product functions the user likes to have, and so on. Okay, this is another type of search engine. It's a for sale house search engine. We captured this from realtor.com. And here in the search engine, you can specify the location, price range, and number of beds and number of baths you are searching for in houses. For example, if you search for houses in Chicago, Illinois, and the price range you prefer is between $200,000 and $500,000, and you'd like to have 3 or more beds and 2 or more baths, if you submit these queries, the system is going to return like here over 3,500 houses that exactly match your query constraints. This 3,500 houses is obviously too many to visit one by one. So what can we do? Narrow down this query. One way to narrow down this search result is you just narrow down your query constraints to reduce the number of results. But if you make your query constraint more strict, you may miss your dream houses, for example, whose price is like $199,000, right? So basically, it needs to design more intuitive and more careful interfaces to interact with users to catch users' preference more accurately. So search is still an open problem. Okay, this is the well-known PubMed, popular search engine for life science articles, right? So basically finds all these life science articles that contain the search keyword. For example, if you type like breast cancer, it returns over here 160,000 articles, right? You can rank these articles based on publication date, author names, and journal names. But finding this related information from this large amount of articles is not easy. It takes a lot of time. For example, let's see this example. Like this is an old TV series called House, and probably many of you watched this TV series. And in this series, this doctor asked his colleagues to find all the causes for neck pain. And here, his colleague opens a PubMed website and typed neck pain here, neck pain. And it returned over 2,600 articles. And he is now reading through these articles to find all the causes for neck pain. This reading one article takes a lot of time, right? So he himself having a neck pain while he's trying to find the causes of neck pain. Because the search takes so long time. So, finding related information in PubMed is still a non-trivial task, because even with the same keyword, different users may like to search for different information, such as like a recent treatment for neck pain or related genes, neck pain, and so on. So we developed a relevance feedback search engine called PubMed. Here in the relevance search engine for RefMed. It is called RefMed. So RefMed user types the keyword the same way as PubMed. Here we typed breast cancer and returned like over 200,000 articles. And the user may read the first few articles and give a feedback on each of them by marking whether each of these articles is highly relevant what he's trying to search, or partially relevant, or not relevant at all. Then once the user pressed this push feedback button, it computes the user's preference or relevance function and returns the top K result among these 200,000 articles. So these are the results, the previous query, relevance feedback query. So if you look at the second and third articles, these are actually those articles that the user marked as relevant, highly relevant. But if you look at the first one, these articles is something found by the system as the most relevant, but the user missed. So to develop this kind of search engine, we needed to develop machine learning technologies, develop an accurate rank learning algorithm to induce an accurate ranking function from a small amount of feedback. Also, we needed a database technology to find the top K result according to the machine learned ranking function. And these two types of technologies must be seamlessly integrated to develop this search engine. Okay. Second type of search engine I'm presenting is a vehicle black box video search engine. Black box. The black box, what is black box? Black box is a camera. It's a camera that keeps recording the front scene and back scenes of a vehicle while you're driving a vehicle. I find that this black box is not very common in America, but surprisingly, these black boxes are very common in Korea. Almost every vehicle are installed with this black box. Because, if you install this black box, you will get some discount on like car insurance in Korea. And in case there's some accident, this video can be used as a proof of accident that you didn't. It's not your fault. Black box video also can be can be used for various purposes to find a recording of car accident that occurred at specific time and specific location. And also this video can be used as a street view application or augmented reality to preview some places. So we developed some algorithm and system called GeoSearch. So while you are driving this vehicle from this way to this way, your black box may capture these scenes. Suppose you like to search for the video capture that captured this building here, and actually this building is captured by these three scenes record, right? Scenes. And there could be another vehicle coming from another way, from here to here. And black box of that vehicle also may capture this building from some scene to another. And if you user submit a query about this building, this GeoSearch automatically finds these corresponding scenes as a result. So this GeoSearch system, it supports point queries and this range queries on the map. And so here are some examples of results, and we developed a new spatial indexing method that returns this result faster than R3. Okay. Now let's move to data mining application. So previously I introduced search applications, and now I'm going to introduce some data mining applications. And especially I would like to introduce an interesting issue in recommendation research. Recommendation it's highly demanding data mining task in industry. So it can be as many applications also in like biomedical informatics. This recommendation this research has been started in the movie domain, first place, movie domain. And there's like HCM conference called RECSYS, which is a top conference in recommendation area. And this RECSYS stands for Recommendation System. This recommendation system has various applications in various domains, but as I said, it first started at the movie domain, and so it is used for recommending movies to users. And, there's one problem of this typical recommender system is, they like to recommend popular items to users. There was a competition recommendation initiated by Netflix company. It was called Netflix competition, where this company Netflix, they opened some of their data to public and let people develop their own recommendation engine. And Netflix awarded a lot of money to those who developed the most accurate recommender system by evaluating their prediction accuracy. But it turns out that the most accurate system tends to recommend popular items. Recommending popular items, you cannot say it's effective, because if the item is popular, then users likely already know the item, likely have pre-made decisions on the purchase of item even without the recommendation. For example, recommending Star Wars or Titanic may not be an effective recommendation. So the accuracy was high, but the effectiveness is not high. And then, what is effective recommendation? Effective recommendation must recommend unexpected, novel items that could surprise users, affect the user's purchase decision. So there have been research on novel recommendation, but still, this novel recommendation system, still they like to recommend popular items. So we analyzed a public movie database such as IMDb in order to see whether most users are likely to watch popular movies. But we found that there are personal popularity tendency. Here is a personal popularity tendency graph. We drew this graph over 900 users that we found from the web. And as you see, different users likely to have different style of personal popularity tendency. Here, user 265, this user likely to watch popular movie. Its axis is the popularity of the movie. But user 585, its popularity tendency is rather flat, right? Based on this individual popularity tendency, we developed a novel recommendation algorithm that considered this personal popularity tendency as well as this prediction accuracy. And it turns out that our algorithm improves the prediction accuracy, coverage, as well as this diversity of recommendation. Finally, I'd like to address a new issue in recommendation, which is recommendation timing. We proposed a framework that determines this recommendation timing as well as the recommendation items. I'm going to skip this due to the time limit, so I think I'm supposed to present this for 40 minutes. I have a couple of minutes left, I think. And after that, actually, we are working on this scaling up these algorithms for matrix factorization and recommendation, and also we are also working on this recommending. So another issue is a cold start problem. Cold start problem is a problem in recommendation. When a new movie comes out, there's not enough log information accumulated. So in that case, how do we make recommendation on such cold item? These are what we are working on currently, and so here's ongoing projects in my lab at POSTECH. We are working on live log machine learning, mining unstructured data, and personalized recommendation system, mining network log for security, and cancer subtype detection and prediction. We are working with some Catholic hospital in Korea. And these are all application level of research. And for the platform level of research, we are developing like big data processing platforms for video and multimedia data, and also developing big graph processing engines. In POSTECH, we have 300 nodes of clusters that we are using for this big data research. Here, there are some facts on POSTECH. There's some ranking at the times, ranking of World University. And we ranked #1 in the World University of under 50 years old, 2014. And we have the largest research funding per faculty among the universities in Korea. And the undergraduate students are top 1% in high school in Korea, and we bilingual campus, we have to teach every course in English. About 40 students and 40 faculty members in the campus. Okay, I think this is it for my presentation. I will take questions from now. Thank you.
We're going to unmute all lines right now and open for questions.
Okay.
The conference has been unmuted.
Okay, any questions for Hwonjo? Okay, I think I have one. So, Hwonjo, have you talked to our core development team on how your work could be integrated or have a collaboration with bioCADDIE?
So this bioCADDIE, one of the sub-projects in the bioCADDIE is to data recommendation, right? So
yes, the pilot project 2.2, yeah.
Yeah, data recommendation. So usually one of this work is joint work with Professor Xiaochen Jiang. This parallel matrix factorization algorithm. The matrix factorization is, one of the most accurate algorithm for making a recommendation. And if the size of data is too big, it takes too long to make a recommendation. So we developed this parallel algorithm for this matrix factorization to speed up large data. So this is also joint work with Professor Xiaochen Jiang at UC San Diego. And also, there are many issues in recommendation, in data recommendation bioCADDIE project. So recommendation part, I think, could make a contribution. I'm working with Xiaochen Jiang currently in that subject.
Okay, thank you.
Today, mainly I presented this general technical issues. What issues are going on in this big data world, the technical perspectives.
Okay. Yeah. Any other questions for Hwonjo? So I can see Jeff here in the room. Jeff, do you have any questions on the technical part?
I missed a little of the beginning, so I sort of came in a little late because of some issues I had to take care of. In terms of the recommendation, the question is how can we, potentially, leverage some of the recommendation strategies, as we get to developing the UI. So there are some potential, future avenues where we can, keep dialogue open. So.
Okay.
Okay, so I think if we don't have any other questions, I think we can end up a little bit early this webinar. So I would like to thank you, Dr. Hwonjo, for this great presentation today. And the next webinar is going to be on August, I think it's 13, and all the information is posted in our website. Okay, thank you.
Okay, thank you.